Alright, welcome back. This is the video solution for problem 2 from the third quiz. So here we've been asked to compute the Laplace transform of cosine of 3t. But we're not just told to do it any old way we want to. We want to use the definition of the Laplace transform. So that means we actually have to know the definition of the Laplace transform. Probably a good idea. I mean, Laplace transform is in the name of the course. So let's see here. So the Laplace transform of the cosine of 3t is defined as an improper integral from 0 to infinity, cosine of 3t. Okay, and then we multiply it by the decaying exponential, e to the negative st. All right, so this is an improper integral. Okay, first thing we're going to want to do is find an antiderivative. So I call that my f prime of t. So f prime of t is equal to cosine of 3t e to the negative st. And I want to find f of t. Oh man, this looks like it's going to be another one of those integration by parts problems. Ugh, man, I don't want to do that. Huh, that's interesting. I highlighted the first sentence, but I don't think I highlighted the second sentence anywhere. Why not? What? I didn't read that. What did that say? It says you may freely use that an antiderivative for e to the at times cosine of bt is this. Whoa, hey, that's a game changer. I don't have to compute an antiderivative for this. They're telling it to me. The only thing I have to identify is what's the b and what's the a. Well, let's see. It's cosine of 3t, so my b must be 3, and it's e to the negative st instead of e to the at, so my a must be negative s. Hey! All right, so I can just use this formula. So my antiderivative should be e to the at, but a is negative s, so e to the negative st over, okay, a squared, okay, but a is negative s, so s squared plus b squared. Oh, but b is 3, so this is 9. Okay, and then I'm going to have 3 times the sine of 3t plus, oh wait, a is minus, so minus s cosine of 3t. All right, that's pretty nice. So once I've done that, now I know I'm going to have to compute what happens to f as t goes to infinity. Okay, remember we abbreviate that, right? So if I write limit as t goes to infinity, f of t, we're abbreviating that as f of infinity. All right, and then we want to know also what f of 0 is. So let's see. As t goes to infinity, what happens over here? Well, note, we have a decaying exponential, right? So a decaying exponential divided by s squared plus 9, which is just a constant. So that's not actually going to change as t changes. Times, well, I have a constant times a sine function and a constant times a cosine function. And sine and cosine are bounded functions, right? Add them together, it's still bounded functions. So this is a decaying exponential basically times a bounded function. And we know that the decaying exponential, right, provided that our s is positive, right, that's why it's decaying. So let's assume s is positive. We know that this is going to go to 0. The bounded function is just between some finite bounds, and you divide by a constant. So as t goes to infinity, this decaying exponential is going to kill the bounded part, and the constant can't change that. So this should be 0. Okay, so that's the intuitive explanation. If we wanted to make this very, very precise, right, we would use the Squeeze Theorem. So by the Squeeze Theorem, the limit as t goes to infinity, and let me just ignore this constant, just the same, save a little time, e to the negative st times 3 sine of 3t minus s cosine of 3t equals 0. All right, so we could go into the details more if we wanted to, but let's not here. All right, so then we have minus f of 0 So at 0, what happens? We get 1 over s squared plus 9. And then let's see, sine of 0 is 0, so this term dies. And then cosine of 0 is 1, so we get minus s. So times negative s. Hey, we got a minus, and a minus is a plus, and so we get s over s squared plus 9. There is our Laplace transform.